Hey, what's up, everybody? Mr. Murray here, Mr. Murray's Mathland, and we're just doing a couple other natural log problems that apply to tangent lines. So in video one, we showed how to get the derivative of a natural log function, and now we're just going to apply it to a couple tangent line, classic tangent line types of problems, just for a little extra practice here. So number one, we'll just jump right in here. Write an equation for the line tangent to this function at x equals 6. So, if you're in my class or if you've been watching these videos, and, for all 7 of you out there who do that, um, here is, you hear me say this a lot. If you want to write the equation of a tangent line, you need two things, right? You need a point and the slope. So the point, they've given you the x coordinate for the point of tangency, but we need to get the y coordinate, so we're going to plug 6 into the function. And so that's going to be ln of 6 squared, which is 36, minus 6 times 6, which is 36, plus 1, and with a plus 4 after the log. We simplify that, and we get to ln of 1 plus 4, and hopefully everybody's thinking right along with me that, hey, ln of 1, that's a value of 0, right? Because that's saying e to what power gives you 1, and so that's the 0 power. So 0 plus 4 equals 4, of course, and so our point of tangency is 6 comma 4. Okay, so we got that point, hang on to that, and now we need the slope. And so if you've come this far in calculus, you know the slope comes from the derivative. So the derivative of this function will be y prime equals, and taking the derivative of a natural log, you do 1 over that quantity, 1 over x squared minus 6x plus 1, multiplied by that quantity's derivative. So the derivative is that is 2x minus 6. And, just to focus, not ignore things, there is this plus 4 on the end, but the derivative of that, of course, is 0, being a constant. So that's it for the derivative, but watch out if there had been like an e to the x or some additional stuff there on the end. So that is your derivative, but remember, that's just the slope function. So if you want the slope at 6, you got to actually plug in 6. So when we plug in 6 to this, 2 times 6 is 12, minus 6 over, and again in the bottom we get that same, 36 minus 36 plus 1. And of course, if you can do some of this in your head, that's fine. You're going to get 6 over 1, which is really just going to give you 6. So that is your slope. And so your tangent line is y minus 4 equals a slope of 6 times x minus 6. And if you want to use a slope-intercept form or some other version, that's obviously fine. But there's one version of the tangent line. Okay, so pretty straightforward. Just a little practice with the ln rule. And here's just one more here that has to do with tangent lines. And this is like a classic calculus problem that every time you learn a new derivative rule, you tend to see this kind of question. For this function, find where it has, if any horizontal tangent lines. And you know that you're looking for essentially spots where the graph turns around, relative maxes, relative mins, or maybe any saddle points, just places where the graph is flat, or it's got a horizontal tangent line. And so the strategy is always the same for these kinds of problems. You're going to find the derivative and set it equal to 0, because you're basically going to ask, when does this have a slope of 0? Okay, so of course the first half of the battle is getting the derivative. And so you're doing the derivative of f of x equals x to the 4th ln of x. Hopefully you're recognizing that this requires the product rule. And this is, a fairly straightforward product rule to do, but however you like to get that done, you have the two functions to worry about. You have x to the 4th, and its derivative will be represented. That'll be 4x cubed. The other function is, of course, ln of x, and its derivative is a nice, simple 1 over x. So when you use your product rule, these inners plus the product of these outers, you're going to get 4x cubed ln of x plus, now when you multiply this x to the 4th times 1 over x, It actually works out kind of nice. You get x to the fourth over x, which reduces to x cubed. And that's actually, if you're thinking ahead, going to make our solving work out a little nicer. And now we're going to set this derivative equal to 0 and see if there's any x values where this is equal to 0. And factoring is one of the classic things we use to solve these. So let's look for that greatest common factor. We can take out x cubed, and then we will have 4 ln of x plus 1. And when we set each of those equal to 0, you're going to get a solution of x equals 0. And here you're going to get a solution of, well, ln of x equals negative 1/4 when you subtract 1 and divide by 4. And then to solve for x, if you're a little rusty with your ln's, this is where you can raise e to each side, or it's called exponentiating the equation, because that's the inverse operation. That will leave you with x on this side, and you get e to the negative 1/4. It's really just taking your thing from log form to exponential form, if you like to think of it that way. And we tend to not like negative exponents, so we might write that as 1 over e to the 1/4, or 1 over the fourth root of e, if you like. So we got two x values here, that solutions to this equation, but if you're thinking ahead that you look to this direction and we want any points, that generally means we want the coordinates, the ordered pairs, so you're going to need the y coordinates. And I hope, well, maybe not, I don't know, but if you were to go and plug 0 in, you'd get 0 times ln of 0, and ln of 0 is undefined. So if you're, it's been a while since you've done some things with logs, like since last year in pre-calc, you might take note of these kinds of things, that the domain of a log function, remember, is that the inner expression, the argument of the log, must always be greater than 0, can't be equal to 0 even, because then you're saying e to what power gives you 0, and nothing exists. So, x equals 0 is not in the domain, so it's not going to be a valid solution here. And we're only looking for values that are positive, and 1 over e to the 1/4 is a positive value. So that's a solution. We just now have to get the y coordinate for it. And like I said, if you didn't think about the domain right off the bat, hopefully you would notice when you went and plugged in 0. But if you were a little careless, you might plug in and think 0, 0 was the point there. So just watch out for those kinds of things. Logs have domain issues. And so now we're going to plug this 1 over e to the 1/4. We're going to plug this back into the original. And so that means the function is x to the fourth ln of x. So you get 1 over e to the 1/4, or if you want to think of that as 1 over the fourth root of e, that's going to make this part look nicer for you, times ln of 1 over e to the 1/4. And it's actually, kind of a nice little simplifying algebra practice here, that 1 over the fourth root of e raised to the fourth is going to be 1 to the fourth is 1, and the fourth root of e to the fourth is just e, multiplied by ln of 1 over e to the 1/4. And this can also be simplified a little bit and might help you to visualize putting it right back to e to the negative 1/4. Helps you to see that, because remember, ln and e are inverse operations, so they cancel each other out. Ln of e to the x is always that x value. So you get 1 over e times negative 1/4. And that, of course, will give you negative 1 over 4e. So your coordinates, I would say, in the nicest form possible, are 1 over e to the 1/4, or again, fourth root of e, comma, negative 1 over 4e. And there is 1 point, and those are some very small decimals. And just as a little confirmation here, you could always check the graph out on Desmos or on your TI calculator. And there is one minimum notice, and notice that domain, of course, it doesn't exist to the left of 0 or even at 0. Well, this says it does, but Desmos has issues. But this little minimum here, 0.779, negative 0.092, that's this point in decimal form. And so there we go. So hopefully you saw a couple problems, brushed up on your calculus, but also some pre-calc properties, and all good. If you have any questions, just let me know, and keep calm and do calc, kids. See you later.